Who hasn't had this situation happen to him? You're walking along, it's a fine day, and suddenly you fall down. And you've fallen, and you're hurt. And you can't get up, and you need to call for help. But you don't have a cell phone. Why? Because you left your precious cell phone with a friend of yours. But fortunately, your friend has a new shoulder-launched cell-fire missile. So, how does that work? Well, here it is. It is a lightweight shoulder-launched missile that launches your cell phone at you. Pretty smart here. By the way, just in case you're wondering, this is question 4.3.2. 4.3.2, and it's, of course, the only problem. Problem 1 so far. So, this is quite a remarkable tool. This rocket weighs only 200 grams and can produce a remarkable 50 newtons of thrust. Very nice. Which is going to help accelerate your cell phone to you, where hopefully you will be able to reach out and catch it and call for help. Because your buddy can't help you. Your buddy's like 20 meters away. This has got to happen. So it's going to launch. Now, we've dealt with horizontal projectile motion before. Things rolling off of desks and doing other things. This is different because, yes, it's coming towards you, but in this case, your object is going to be accelerating. It's going to be accelerating using Newton's second law of motion. F equals ma. Now, let's just figure out how fast it's going to accelerate. And we'll start dealing with projectile motion stuff in a little bit. This is all from last chapter. I'm sure everybody remembers everything from last chapter, yes? So, the rocket. So the force is 50 newtons. And the rocket itself weighs 200 grams. Now, F equals ma, we're going to be using kilograms. We're going to change grams to kilograms. 200 grams is 0.2 kg. But the rocket's not the only thing with mass, is it? Your cell phone has some mass. So you got to add that in 2. So 0.2 kg plus the weight, the mass of your cell phone. Mine comes in 0.1588 kilograms. So that's your total mass. The mass of the rocket plus the mass of your cell phone. And we're trying to figure out A. So, putting it together. By the way, your cell phone is probably not the same as my cell phone. So 0.2 plus 0.1588 becomes 0.3588 kg. Now, in order to get acceleration by itself, you got to divide both sides by 0.3588, 0.3588, and we find out that 139 meters per second is going to be equal to your acceleration. Meters per second squared is going to be your acceleration. So that's your acceleration. It's pretty good acceleration. I told you this thing was handy. By the way, 50 newtons, that's exactly tested. That's exactly 50 newtons. Just in case you were wondering. It pilots out exactly 50 newtons. Now, we've never dealt with this before. We've never dealt with a horizontal projectile which is accelerating. They've always just been moving at a constant speed. In this case, the speed is changing. But one thing we do know is no matter how fast you're going, everything falls at the same rate. Everything accelerates downward at 9.8 meters per second. It doesn't matter if you're a rocket, if you're a mouse, if you're a giraffe, if you're a rocket riding a mouse, on a giraffe, it doesn't matter. So everything falls at the same rate. So let's just do some calculations with that. Now, the height from your shoulder, it just so happens that your friend is exactly my height. Well, my friend is exactly, your friend will be exactly your height, okay? Your height at the shoulder is on your biometrics page, right? My height at my shoulder is this. Well, anyway, let's look at our formula. Delta x is equal to 1/2 ay, or sorry, not delta x, delta y is equal to 1/2 ay delta t squared. We're trying to find delta t because if we can find out how long it's going to take to hit the ground, we can find out how far it's going to go in that time. That's the key here. So everything's going to take the same amount of time to hit the ground no matter how fast it's going. Well, assuming it falls from the same height. So ay, in my case, my height at the shoulder, comes in at 1.63 meters, and that equals 1/2. What's ay, earthlings? That's right, 9.8 meters per second squared. And then we're trying to find delta t squared. Well, we're trying to find delta t, but in the formula is delta t squared, okay? So, 1.63 meters is equal to half of 9.8 is 4.9 meters per second squared times delta t squared. Divide both sides by 4.9 meters per second squared. 4.9 meters per second squared. They cancel. Now, doing this, I get 0.33 seconds squared equals delta t squared. Take the square root of both sides, and I get, what did I get? 0.58 seconds equals delta t. So now we know delta t. We know delta t. Let's apply this to our formula. Now, does anybody remember a formula for how fast or for how far things go if they're accelerating? You're probably wondering, what is that formula? Actually, as strange as it sounds, we've already used it. We use this formula to figure out how long it takes for things to fall a certain distance. Falling is accelerating, just like this is accelerating. Same formula. We're just going to use it for delta x now. So, different color. Oh, does this work? I guess it works okay. Okay, so we're going to do the same thing over here. Define delta x. Define how far away this thing is going to land. Delta x is equal to 1/2 ax. The acceleration in the x direction. Delta t squared. It's exactly the same formula, just we're replacing the x's and the y's. Delta x, we don't know. We're trying to find that. 1/2 ay, well, we figured it out. It's going to accelerate at 139 meters per second squared. And delta t, we figured that out. It's 0.58 seconds. So, how far is it going to go in a little over a half a second? Delta x is equal to 1/2 of 139. I don't know, but I wrote it down, didn't I? Roughly 69.7, well, from my calculations, meters per second squared. Square this. Hey, you know what? We already have the square right over there. 0.33 seconds squared, times 0.33 seconds. So we multiply these two together and we get delta x is equal to approximately 22.99 meters. Now, we only have 2 sig figs here, we only have 2 sig figs here. We got 2 sig figs. So basically, we're going to round this and find out that delta x is equal to approximately 23 meters away. That's where it's going to land. Now, by the way, your numbers are going to be a little bit different. If your cell phone is lighter than mine, you're going to accelerate faster, right? If your cell phone's heavier, you're going to accelerate slower. So your acceleration might be a little different. Probably your delta t is also going to be smaller. Why? Because I'm 1.63 meters at the shoulder. You're probably a little shorter, which means it's probably not going to take quite as long for something to get to the ground. So your delta t might be a little bit smaller, but I would expect it to be somewhere in the same neighborhood. So anyway, go ahead, give it a go, and hey, send me the results. Thank you very much.